Thank you. Okay, we are on page 96, 96. So make sure your phones are away. How did yesterday's work go? Yesterday's homework was okay? Excellent. If you just came in, you'll want to pick up one of each of these. Okay, 1, 2. Now, we're going to look at situations here where we're not actually at equilibrium yet, where we're going to be moving towards equilibrium. But in these problems, we're starting initially with only reactant present, or possibly only product present, but usually we put only reactant because, whatever. So we are not yet at equilibrium. What does a system do when it is not at equilibrium? It's going to shift until it reaches equilibrium, yes? So we're going to have a shift, and then we're going to reach equilibrium. Now, for these problems, we are going to remember that the shifts are proportional to the coefficients. You already know this because you have been labeling x and 2x, yes? On your graphs, on your concentration graphs, yes? So if we look at this graph here, you can see that SO3 goes up by that much. And SO2 goes down by that much. Do those arrows look about the same size? Yes, and that's because the coefficient of SO2 is a 2, and the coefficient of SO3 is also a 2. So this is a 2x, and this is a 2x. Now the O2 now it starts to get really complicated, which is why we don't draw the graphs very often. We're just going to get into doing the math. The O2, I guess maybe I'll draw this in blue so it looks a little bit different. Here's our O2. It starts here and goes down to here, and that's X. That's our O2. And look, O2, it's half the size and it's got a coefficient of 1 as opposed to the 2x. We are on page 96, 96. I am recording. Look at me go today. Every once in a while I get it together, right? All right, same thing here. You can see we've got we're starting at different points, right? In this one, we start with only SO3. Over on this other side, we started with only SO2 and O2. So this one started with only reactants. This one started with only products. And you could, if you wanted to, go through and say, oh, look, I've got X, I've got X, sorry, 2X, I've got 2X, and I've got 1X. But what do you notice about the final levels for both graphs? Ooh, I made that one way too big. Okay, that's okay. But do you notice they end up at the same levels? And that's because KEQ will always be the same. So it doesn't matter whether you start with products or you start with reactants. The final K value, the ratio of products to reactants, will be the same. Now, they don't always have to be exactly the same values, but the ratios will always be the same, okay? So let's take a look at what we're going to actually do with this. So initially, we have 2 moles of NaOCl is placed in a 1 liter flask. So initially, we have 2 moles of NaOCl in a 1 liter flask. So what that means is our initial concentration of NaOCl is how much? 2 molar. Okay. So we place that in a flask. Usually you will be given a temperature just to let you know that the temperature is constant. It really serves no purpose. So you can basically just ignore it. Don't try and do anything with the temperature. There's no point. Okay. Now, when equilibrium is established, so now we are at equilibrium, we have 0.66 moles of NO. So what is the concentration of NO at equilibrium? Tell your partner. We have 0.66 mole. What's the volume? Still just a 1 liter flask. That means, oh my gosh, what easy math is that? 0.66 moles in 1 liter is 0.66 molar. And we're going to use a little tool that makes solving these problems really easy to do and really easy for a marker such as myself to follow your work. Okay? And that tool that we are going to use is called a Rice table. All right? R stands for the reaction. I stands for the initial concentration. C stands for change in concentration. And E stands for the equilibrium concentration. So this right here is our shift. Oh, look, I labeled it already. Ha ha ha. Okay, this row represents the shift. So what we do is we take the information that we are given in the question and we see what we can figure out. All right, so we look and we say, what information do I have? I have the initial concentration of NaOCl, so I can put that here, 2.00 molar. What else do we have? Do we have any other information that can go in that table? We have concentration of NO. Now, is that initial or equilibrium? That is at equilibrium. So we're going to want to put that. Now, if you want to, you can draw little lines here to separate them. It's not required, but sometimes it just makes it easier to see things. Okay. So our equilibrium concentration of NO is 0.66 molar. And to be honest, we actually know 2 other concentrations on here. Chat with your partner and see if you can figure it out just from reading it. And they're actually very easy ones. It's not something where you have to do a calculation or anything. Go back to the question. How much NO did we place into the flask? Hold on. How much NO was placed into the flask? None, because if we don't mention it, we did not put it in. Yes? So if it does not say we placed NO in the flask, then initially the concentration of NO is 0. So this is 0 molar. And how about Cl2? How much Cl2 did we put in initially? 0, because again, we did not say we put any in, so it's just 0. Now, if you have 2 of the 3 things in a column, you can figure out the other one. So in this column right here, we start at 0, we finish at 0.66. Did we go up or down? We went up, so this is plus 0.66, right? 0 plus 0.66 is equal to 0.66. Now I'd like you to think, are we going to put a plus, or don't write this down, a plus or a minus sign for the NOCl? Are we going to put a plus or a minus sign for the Cl2? Tell your partner. There's a couple ways to figure this out. What do you guys think? Plus or minus for the NOCl? Minus. You can say, well, it has to be negative because I'm starting with only this. Which direction does the reaction have to proceed? Right. It has to proceed to the right. And if it's proceeding to the right, we are using up NOCl. So that's going to be minus. And our equilibrium arrow is here. So what sign are we going to see for the Cl2? It has to be positive. Could it possibly be negative? Can we go down from 0 molar? No, we absolutely cannot. You cannot have a negative concentration. That would mean like antimatter or something weird like that. I just don't know. Okay. Now, we have coefficients of 2 and 2 and 1. What value should we put in the NOCl box for our change? We have a 2 and we have a 2. So it's a 2 to 2 ratio between NO and NOCl. So 0.66, because if you use up 2 of these, you make 2 of those. If you make 0.66 NO, you've used up the same amount, 0.66 NOCl. Now the coefficient of Cl2 is a 1. So how much Cl2 are we making? 0.33, because we're making half as much. For every 2 NOCLs, we make one of these, so it's going to be half as much. So that's 0.33 molar. And then we simply add or subtract down the columns. So 0.2 minus 0.66 is, sorry, 2 minus 0.66, 1.34 molar. And then over on our right-hand side, we have 0 plus 0.33 gives us 0.33 molar. And now guess what we have? We have equilibrium concentrations. Yes? And we have been, what have we been asked to find? We have been asked to find, we're told to calculate the KEQ. If you are given equilibrium concentrations, can you calculate the KEQ? Yes, because you did that yesterday. So do the work, and then you can check the work with me and see if you would get full credit. Okay? Yes. Do you need to put these in, do you mean? Oh, the value before rounding, you do not have to, okay? I like to show it so I can say, oh, here's how we round, but you don't have to. You can go straight to the rounded value. Now, how would we round this? 0.080 or you could write it as 8.0 times 10 to the negative 2. What is the unit of KEQ? Nothing. There is no unit for KEQ. Okay, very good. Now, one thing I'd like you to take note of here, not that it matters in this case, but you see how we have 2 sig figs here? Yes, in the 0.66. How many sig figs do we get in the answer? 3 sig figs. So that might come important later. Like say the other ones had been 3 sig figs and you're like, oh, but I had a 0.66, therefore I'm limited to 2 sig figs, but you are not, because subtraction goes to the decimal place. Okay, it doesn't matter in this question because we got some 2 sig figs over on the other side, but sometimes it will. Probably on your quiz, there will be one like that. Just saying. All right, a rice table is the accepted method of showing work. Okay, AP uses it, universities use it, I use it. If you do not show a rice table, you will not get full credit. Do we understand each other? Okay, it's like if you don't write KEQ equals, you're going to be losing some marks, except for a rice table is usually worth 1.5 to 2.5 marks. So that's a lot to lose if you're not writing it. So let's try number 2. Actually, do you guys want to try number 2 on your own? Yeah, try number 2 on your own. See what you get. Okay? And notice I've gotten rid of I've just written square brackets around ICE to show that we're finding concentration.
Okay, so we start with some of this and then the top. So the reaction go fast. So it's using up this. It's using up a negative. Okay. Okay. Oh. No, yeah. Yeah, and you need to put up like through. Yeah. So we find that you do it up here, but when you do it on the test, you have to. You're like really low. Okay, so over here, what we've got some of this, none of this, and this. So which is the reality? So it's fast to go to the right. So that means when you do this up, you want to do this. If we're using this out, we're taking some away to go. And if we're making use for this, we're adding more, right? So put it out, so it's really positive. So this much, we don't have any of those, so we have to be doing this. Uh-huh. We're just showing what happens eventually, because eventually we have what we do. Yeah. Yeah, we're saying this system will end up at 4 years. Yeah. Okay. So now our change, because we started with only reactions. Yes. So this one is. And what will add to 0.5. And now you can say, use that as a one-to-one. So if I make 1.5 piece, ratio to 1.5, yeah. Yeah. You should get this. Something. Anything can help. You can smell so. They let that. Here. See something. Yeah. Because how do you like that? It takes. Are you kidding me? What's the molar mass? 71 point. No, 0. Okay. Okay, your issue if I was marking this, I'd be like, I see no calculation for how you got this number. Or like this note. See over on the left there, we've got grams of Cl2, I'm just finding moles, so you would want to show that, okay? I should have made that bigger. That's the one we reached there. And it's not just 71, it's 0, 0.3, so that's gonna be different. So when you write, you try and write the correct sig so that you know these are because it should be not right, like that part? Yeah, I know. Hi. Yes. Yes, but no. Now, we're looking at right? But we don't have the right units here because we're not okay. Okay, things I'd like to point out to you, mostly about sig figs. Also the fact that I left out the molar in the rice table. Writing molar in the rice table is optional because we are using it to get to a KEQ. It's totally fine to write it. You can totally put it in, but you don't have to. And sometimes you're running out short of space, so you might not want to. Okay, but it's totally fine to put it in. And the one thing I'd like you to notice about sig figs, and I did not make this big enough to really see, the molar mass of Cl is 35.5 grams. So if I add 35.5 and 35.5, I get 71.0. So make sure you write 71.0 so that you know you have 3 sig figs at the end. Because of the periodic table we use, you will always have 1 decimal place in your molar mass, okay? Because all our molar masses on our periodic table go to 1 decimal place. In university, you might have variable ones, but you'll have to deal with that then. You do not need to deal with it this year, okay? Excellent. Let's try another one. So anytime. Now, part of the problem is what's going to happen is on the test and on the quiz, sometimes you'll be given a situation where you're already at equilibrium. Sometimes you'll be given a situation when you are not yet at equilibrium. You need to be able to tell the 2 questions apart by reading them. So here is the hint that you need a rice table. Anytime you have only reactants or only products, that's going to tell you, oh, if I have only reactants or only products, I am not yet at equilibrium. Therefore, I need to use a rice table. If you see the words allowed to come to equilibrium, were you at equilibrium? If you are allowed to come to equilibrium, you are not yet at equilibrium, yes? If you have things that are allowed to react, you're still not at equilibrium yet. So you're not at equilibrium yet, so you would need to use a rice table. Okay, so anytime you are not yet at equilibrium, you need to use a rice table.
Okay, example 3. Look at this. Let's take a look and see, is this a not yet at equilibrium question, and how can you tell? I'm going to let you read it and see if you can figure it out. What do you guys think? Are we at equilibrium or are we not yet at equilibrium? We are not at equilibrium. How can you tell? We have allowed to come to equilibrium. And also, we have only reactants, right? We have N2 and O2, only reactants present. And remember, if you have a system at equilibrium, you will have both reactants and products present. So we are not yet at equilibrium. What tool should we be using? A rice table. Do you guys think you could start by drawing yourself a rice table? Okay. You can try and do it without me, and then you can check your answer when you're done up here, okay? Now you might find that you get to this point and you're like, I've got these changes here. I know that these two are going down because I have some. And over here I have none. So the side that has none has to go up. And the side that has some has to go down. But unlike the other questions we've done where we had an equilibrium value, do we have any equilibrium values here? No. What did you call it when you were drawing concentration diagrams and you were saying this is going to go up by a certain amount and that's going to go down by a certain amount? What did you say about those? You said this one goes up by X and this one goes up by 2X, or this one goes down by 3X, or whatever. So if you don't have an equilibrium, you can use X for your change. And so what you do is you say, I have a coefficient of 1 here, so this is going to be 1x, just x. I have a coefficient of 1 here, so this is going to be x. And I have a coefficient of 2 here, so this is going to be 2x. So now we add our way down or subtract our way down, 1.00 minus x, 1.00 minus x, and then 0 plus 2x is 2x. Well, that's great. Now I've got some x's. It's my unknown. What tool could I use to help find x? I can do some algebra. Well, what am I going to do algebra on? What tool should I use at this point? I've got a Rice table. Now I want to write the KEQ expression. So KEQ equals. Should you start throwing in the equilibrium values, or should you write your concentrations first? Write your concentrations first. Now, it would be really tempting here to like solve this, but there's nothing really to solve for yet because x's are all over the place. So let's see, we can't solve for this unless we were given a KEQ because we cannot have two unknowns, right? So let's go back and see, were we given a KEQ value? Thank heaven, yes. Okay. KEQ is 4.51 times 10 to the minus 3. So we plug that in, 4.51 times 10 to the minus 3 is equal to, and then we start plugging in our equilibrium concentrations from up in the Rice table. So we have 2x squared. Do you like how I wrote that? What do you think? 2x squared like that? I've got 2x, and I'm substituting that in for my NO. What have I done wrong? I need to have brackets because I need to square the whole thing, the 2 and the x. Yes? Because the concentration is 2x, so I need to square the whole thing. And then down on the bottom, I have 1.00 minus x times 1.00 minus x. Now, if I started doing some gross algebra on this, I could get myself a beautiful quadratic equation. Do you guys love solving quadratic equations? If you do, I'm sorry, in Chemistry 12, you are not required to solve any quadratic equations. You will always be given a situation where there is a sneaky shortcut. Can anyone see what the sneaky shortcut is here? How can I avoid using a quadratic equation? I got one person who knows. Anyone else know? Got two people who know. If both things on the right-hand side are squared, what can I do with it? I can take the square root, which will get rid of that squared term. If I do that to the right-hand side, what do I have to do to the left-hand side? Also take the square root. Oh, 4.51. Thank you. 4.51. Root, 6716. 6716. Thank you so much for keeping me from that nasty little error there. Now, do you guys know how to multiply this out here? Yes, we get 0.06716 minus what? What do I get when I multiply 0.06716 times x? 0.06716x, right? It's not rocket science. 0.06716. X is equal to 2x. How much of this algebra do you need to show? As much as you need to do to get it correct. I'm going to show you every step because it makes it easier to follow along. Okay, but you don't need to show every single step as long as you get it correct. 0.06716 is equal to 2x plus 0.06716x. 2.06716 n equals 0.06716 equals x equals 0.06716 divided by 3.067 equals 2.067 equals 0.03249. Am I done? Once I've solved for x. Have I gotten x correct? Did you guys get the same value? 0.03249? Because you know me, I tend to make mistakes. Did I get it correct? Or are you getting something different? You got the same? Did you get the same? No. Okay, so here's the deal. In terms of keeping sig figs as you go along, I actually probably should have kept one more because I have 3 sig figs here. Yes? In order to be 100% sure I will not get a rounding error, I should keep 2 more digits than the number of sig figs I need. So I think I did this because I thought it was 4.5, so I kept 2 extra. But if it's 4.51 e negative 3 square root, I should actually point 67157. 67157. Let's see if this makes any difference. 67157. 67157. 5757. 67157. 57. 1. 57. 671. 57. 57.067,157 divided by 2.067,157 equals. Oh, and I still get the same thing. I still get 0.3249, 0.03249. So if you got a different answer, what that meant is you rounded off a little bit too much. Here's the deal. Usually 99% of the time, not 99.99, but 99% of the time, you can get away with keeping only 1 more digit than the sig figs you need. Okay? 1 time in 100, you need to keep 2 more digits than the sig fig you need. I know there is one quiz out there where you need to keep 2 digits. I can't remember which one it is, or even if you'll get that same version. Okay? One of the quizzes this year, maybe. Now, can you keep these things in the memory in your calculator? You can do that. Then you don't have to write out all the digits. Yes, you can just have your calculator keep all those digits. Yes, you guys know about the memory functions on your calculator. If you don't, learn how to use it. Go look up memory function on your calculator. All right? Because it's really handy. You don't have to write out all the digits. Your calculator just keeps track of it for you. At any rate, we got X, but we are not done because what were we actually asked for? Oh, equilibrium NO. And equilibrium NO is right here. So the concentration of NO at equilibrium is equal to 2x, which is equal to 2 times 0.03249, which is equal to 0.06498, 0.06495. And then we say, how many sig figs do we have? Well, there's 3 sig figs here, 3 sig figs, 3 sig figs. That 2 in front of the X doesn't count. So we should have 3 sig figs. So that's going to become 0.0650. Do we need a unit? Yes, because this is concentration. So it's going to be molar. Okay, I am going to assign page 99 for homework, but we're actually going to take a brief look at page 100, okay? So there are 4 questions on page 99. That is your only homework today. Page 99 is the homework. But for now, we're actually going to go to page 100 and start on it because we want to get as much of this done before the weekend as possible. And if anyone came in after the bell and you did not get the overall review for the unit, please come and pick one up. Now, yes, sorry.
For this question, would it be possible for me to just plug in the molarity of the, since I'm given the reactant concentration, I just, slide it to, so molarity will be 1 mole per liter.
Yep.
So take that.
So that's where you put it. You went 1 molar and 1 molar. Did we not do that?
I didn't, no, this isn't correct. I forgot to erase it.
Oh, okay.
But,
Yeah.
yeah, so I can use that to calculate KQ instead of doing this, right? Because I'm given the reactants. So
But then that would be 0.
Is it not 0 for initial? It is, right?
Yeah.
Yeah.
Do we use the initial concentrations in an equilibrium constant?
Oh, right. Just
Ah,
right.
we're not at equilibrium. Okay, so it's not the KEQ. All right. Now, do you remember when we were using the Rice tables, we were given either reactants or we could be given products, and we absolutely know which direction it's going to shift. If all you have is reactants, it has to shift towards the products. If I gave you only products, it would have to shift towards the reactants. But what if I give you a situation where I say, here's some reactants and some products, but we're not at equilibrium? We're going to take a look at the ratio between the products and reactants and say, is that ratio too big? Is that ratio too small? Or is that ratio just right? And if it's just right, we are at equilibrium. That's why I like to call Q the Goldilocks of the equilibrium world. Are you guys familiar with the Goldilocks story? She goes into the house of the 3 bears and she eats the porridge and she says, the bears have gone for a walk and left their porridge on the table. There's a mama bear, a daddy bear, and a baby bear. And she eats the mama bear's porridge and she says, this porridge is too hot. She eats the daddy bear's porridge. She says, this porridge is too cold. And then she eats the baby bears and she's like, this is just right. Q is like that. Is it too big? Is it too small? Or is it just right? Okay. So what we do is with this Q value, the expression is the same as the KEQ expression, except for what? What is different between the KEQ expression and the Q expression? We're using the initial ones here to say, are we at equilibrium? Are we too far towards the products, or are we too far towards the reactants? Okay. So now, if we have Q and Q is too big, okay? So if Q is too big, what that means is that Q is bigger than the KEQ. We are not at equilibrium, okay? Q is bigger than KEQ. Think about it for a minute. Does that mean we have too much product or too much reactant? Remember, KEQ and Q are both product over reactant. Yes? KEQ and Q are both product over reactant. So if Q is too big, that means we've got too much stuff in the numerator and not enough in the denominator. So what that means, so this is too big. In other words, we have too much product. And if we have too much product, which direction do we have to shift? To the right or to the left? To the left. To produce more reactant and use up product. And it's going to shift until the ratio of product to reactant is constant and equal to KEQ. Now, if Q is less than KEQ, that means Q is too small. Yes? It's too small. What do we have too much of? We have too much reactant. And if we have too much reactant, which way will we shift? We will shift to the right to produce more product and use up reactant. Until the ratio of product to reactant is equal to KEQ. Now, what if Q is equal to KEQ? That means that the ratio of product to reactant is perfect, just right. And that means that the system is at equilibrium already. Okay? And that's all we're going to do with that today, because I think we're like 1 minute away from the end of class, right? So page 99 is your homework. If it's 4 questions, that should be fine. Tomorrow we'll finish up with Q. And hopefully your quizzes will be marked by tomorrow. I'm not going to make a guarantee because I'm here late with parent-teacher interviews. So we'll see how much I get done. Okay, I'm going to try my hardest though, because I'd like you to have it over the weekend. Did anybody not get the review? Everybody got the review? Yay!